Intermolecular forces lead to surface tension and viscosity. Surface tension is the tendency of liquids to minimize their surface area. This is something you can try at home. Take a nice clean bowl or cup and put some water in it. Make sure there's no grease or soap or anything. And you can actually float a paper clip or a needle on the surface of the water. It appears to be defying gravity, right? Because metals are more dense than water and they're supposed to sink, but they don't. It's the same phenomenon that allows little water bugs to skate on the surface of the water. It's not that they're floating. Floating has to do with a difference in density. If the density is less than the liquid, then you float. If it's greater, it sinks. This has to do with the surface tension of the water. The water does not want to increase its surface area. In order for this paper clip to go through the surface of the water, the surface area would have to increase. I wouldn't recommend trying the paper clip on gasoline because gasoline's dangerous and it's not going to work anyway. The gasoline has much weaker intermolecular forces and they're not strong enough to support a paper clip. If we look at the interactions between the water molecules, we see that the interior molecules are attracted in all directions to other molecules, whereas the surface molecules are only attracted to the side and down. There's nothing above to attract them. And so they're pulled down. They experience a net inward force. In order for the paperclip to go through, it's going to have to break these intermolecular forces of attraction. Another analogy I like for intermolecular forces is Red Rover. If you guys ever played Red Rover, for those of you who don't know, you get a line of people holding hands, and they on one side of the field, and then you've got a bunch of other people on the other side. And the people in the line say, Red Rover, send Sally right over. And Sally runs across, and she tries to break through the Red Rover line. But people are holding hands. If she's running fast enough, or if she gets a weak point, she might get through, or she might not. Okay? So, the Red Rover participants in the line are the water molecules. They're holding hands at the surface of the water. The strength with which they hold hands correlates to the strength of the intermolecular forces. And how fast Sally is running has to do with the kinetic energy. So if you have a strong Red Rover line, maybe the O-line for the Fresno City football team, right? Big guys, right? Strong grips. It's going to be really hard to get through. The paper clip can't get through. If you have a bunch of first graders, little 6-year-olds, and they're kind of wimpy sometimes, right? Especially little girls, they don't want to get hurt. And so you put a paper clip on top and it'll go right through because the forces that are holding them together are weak. Does that make sense? Mm-hmm. Have you ever wondered why water droplets are spherical? It's to reduce the surface area. A sphere is the geometric shape that has the smallest surface area per volume. If you make a square or some other shape, a cube, it's going to have a larger surface area. So they make spheres to reduce the surface area. Here's a picture of a water droplet. And when you say, well, that's not exactly spherical. No, it's being held on the tip of this leaf. It's being pulled down by gravity, and so it gets distorted a little bit. But here's a cool picture of 3 astronauts on the space shuttle, and that's 1 drop of water. Okay, it's a lot bigger than this drop of water. In space, where there's no gravity, you could make a spherical drop of water that's, 2 liters of water, and you just get it together, and it'll stay in a sphere. Because the surface tension, the intermolecular forces are holding it together, it's trying to minimize its surface area. When multiple droplets of water come together, then their surface area is less than when they're separated. Viscosity is another concept. Viscosity is the resistance of a liquid to flow. Liquids that are more viscous flow more slowly. Think about pouring syrup or honey as opposed to pouring water. It pours slowly, right? Honey is a liquid. We're not going to argue that. It pours, but it doesn't pour as fast as water. Motor oil is more viscous than gasoline. Gasoline is inviscid. It's not very viscous. So the viscosity comes from the intermolecular forces. If you have strong intermolecular forces, then the viscosity is going to be greater. In order for a liquid to flow, the particles have to move past each other. If the Velcro between those molecules is stronger, they have a hard time flowing or moving past each other. They're not slippery, and so they kind of stick on each other. I hope you guys aren't hungry. There's a stack of pancakes. It's looking kind of good. I didn't have lunch yet. Here's maple syrup, and it pours slowly onto the pancakes because the molecules in the syrup are more strongly attached to each other, attracted to each other, than water molecules are. Does that make sense?